good morning in the first place. Welcome to this webinar of this Power and Energy series. The webinar is promoted, as you know, by the Center for Power and Energy Systems of INESC TEC. And today the topic is tools for promoting self-consumption and renewable energy communities. We have three speakers. In the first place, José Vilar, who is a senior researcher at INESC TEC, and then Alexandre Lucas, who is also a researcher in INESC TEC and a PhD student at the engineering faculty of Porto University. So they will be in charge of making the first presentation with a total duration of about 20 minutes. Then we will have a 10-minute question and answer, and you are asked if you have questions to use the question and answer facility, and I will read the questions. And then the second presentation by Alexandre Lucas, who is also a senior researcher at INESC TEC. And finally, we will end with another 10-minute question and answer period. Okay, so let's start. Let's invite José Vilar for the first part of this first presentation for about 10 minutes. José?
Okay, thank you very much, Ronald. Let me share my screen. Hope you're already seeing it. So we will start this webinar with this presentation, which is about integrating energy and flexibility local markets, considering the self-consumption regulation. And we will present myself, José Vilar, and João Melo, as you already said. So this will be the content of the presentation, a very fast motivation, some hints on the regulatory context, some comments also on how the wholesale and the local electricity markets are settled. We will then go to the post-delivery market design, and we will then look at how to integrate flexibility market in this post-delivery local energy market, and we will end up with some conclusions. So the motivation basically was to develop a very simple and engaging local market mechanism for internal transaction in collective self-consumptions or renewable energy communities. And this work ended up with what we call the post-delivery market design. And then the idea was how to integrate the provision of flexibility with this energy market, and this ended up with a proposal of a virtual renewable energy community member, and also on the definition of passive energy transfers between aggregators and suppliers. So if we go through the regulatory context, we will focus on the Portuguese case, but there are many similarities with other regulations, such as the Spanish one or the French one. In Portugal, first, this started with a decree in 2019, which was a first attempt to translate the directives, the European directives, to define the individual self-consumption and the collective self-consumption and the renewable energy communities. And there was also a regulation from the national regulatory entity to set up the rules for the application of this decree. And then in 2022, so very recently, there was a new decree which incorporates the operation of the whole Portuguese power sector, with several relevant innovations related with self-consumption that were missing in the first decree, which basically are the possibility of dynamic allocation. We will see how what is this, and also the concept of hierarchical organizations. This decree also regulates the citizens' energy communities. And the current situation is that we are waiting for a new ERSE regulation, for a new national entity regulation, to set up the rules for the application of this decree. And some comments is that the local electricity markets are not yet explicitly regulated, but they are mentioned, and local flexibility markets are also not regulated. So if we look at the traditional relationship model, we have the consumers that buy the energy to the suppliers, that in turn buy the energy in the wholesale market to the producers. And in this payment are also included the tariffs that go to the transmission system operator and to the distribution system operator. The transmission system operator transport the energy, and the distribution system operator distribute the energy to the final consumers. If we look at the new relationship model, then we have that the consumer becomes the prosumer, and it can share locally energy. But to manage this, the regulation needs to define the sharing rules among these prosumers and to use what it is called the allocation coefficient, so that the DSO is able to tell the supplier which is really the energy that was supplied by the supplier and not locally supplied. And we also have the figure of the aggregator, which is in charge of managing the surplus of this individual or collective self-consumption. If we look at the individual self-consumption, then what we have is a consumption unit and a generation unit. And this consumption unit profits from this generation unit energy by using the public grid or an internal or private grid. In case it is the public grid, then the tariffs of the public grids are applied, and these tariffs typically look at the voltage levels that are used, so that these are reduced tariff compared to the tariff of the energy supplied by the supplier. Any resource consuming needs to have a supplier, and in case there is a surplus of the consumption, this surplus can be managed through an aggregator or directly through the wholesale market. Something which is also common in all the regulation is the concept of proximity, which changes from regulation to regulation, but basically it looks at the voltage level where the resources are connected to, and also, for example, if they are connected at the same substation or not, and this is to allow different resources to belong or not to an energy community or collective self-consumption. In this case, individual, sorry. If we look at the collective self-consumption, the main difference is that we have several consuming units, several producing units. The idea is the same. This generation is used by these local consumption units, and the public grid or an internal grid can be used. In the case of the Portuguese regulation, there is a need of having this GAC entity, which is the entity that make all the relationship with the other entities of the market, the DSO, and manage also the aggregated surplus, and has also to set up contracts in case this surplus is to be sold for the use of the grids with the DSO, and with the DSO in case it sells this in the wholesale market. And what are the allocation coefficients? Basically, the idea is that these productions need to be allocated among the consumption units. In the initial regulation, we thought in the initial Portuguese regulation, it seemed that this production was aggregated and then allocated among the consumption units. But in the last conversation we have with, for example, with the DSO, it seems that what is going to be set up is some kind of matrix allocation coefficients, so that each of these production units is allocated over the different consumption units. The way to allocate in this is by computing this coefficient, and the case of the Portuguese regulation is the possibility of having fixed coefficients that can have time discrimination, but that cannot be updated, for example, considering the consumption measure. There is also the proportional allocation, which is an allocation based on sharing this energy proportionally to the consumption of each of the consumption units. And finally, which is in the new regulation, the possibility of dynamic allocation, so that this allocation is computed by the community herself, and for each 15 minutes. And so it can use, for example, all the data on consumption, and also, for example, the internal trades in case there is some kind of local market. With this allocation, then the suppliers can know if they have to supply energy or if there is a surplus. In case the energy allocated is lower than the consumption, there is a supplied energy by the suppliers, and otherwise there is a surplus. Finally, just from my side, a word on the settlement, and this comes from the fact that initially the dynamic coefficients were not allowed. So what does need this internal settlement in the community? But this means that in case there are no dynamic allocation coefficients allowed, there is a need to compensate these inefficiencies of the coefficients, and this compensation unfortunately cannot be exact. Sometimes there is a surplus, sometimes there is a deficit. And after this internal inefficiency compensation due to the allocation coefficients, there is the compensation related to the energy share, so that those that are owners of the energy are paid by the energy they are sharing with the others. In case of dynamic coefficient, this is much simpler. The dynamic coefficients can reflect exactly what it is going on in the community. And so the EGAC computed these coefficients, send them to the DSO, which use it to inform the suppliers on the supplied energy. And I give the word to my colleague, Joan. So please, Joan, go on.
Thank you, Bilal. So now I'm going to explain this integration of a local flexibility market with a local energy market that is post-delivery. So basically what we are trying to solve here is the problem of the need of transfer of energy between the retailer and the aggregator. And this problem originates from the fact that when an aggregator activates flexibility from a prosumer, it causes an imbalance from the prosumer's retailers, because the prosumer retailer has to buy in advance in the wholesale market what it expects that the consumer will consume. So in this case, in step 0, this retailer associated to this prosumer expects that this consumer will consume 200 kilowatts because it knows that it's going to generate 200 kilowatts but consume 400. However, the aggregator activates 50 kilowatts of flexibility. So in fact, what is delivered to this prosumer is 150 kilowatts. So the activation of local flexibility from the aggregator causes a deviation from the retailer point of view. And this is an issue pointed by the USEF framework, which we use in this proposal of ours. The USEF framework is a very interesting study. They propose several models to deal with several issues regarding local flexibility markets. And one of the issues is the need to transfer energy between the retailer and the aggregator. And we use the contractual model. So the contractual model supposes that there is a contract between the retailer and the aggregator in which this transfer will be solved between them. And what we propose, and what I'm going to explain in the following slides, is a proposition in which we can use the local flexibility market to transfer this, the local energy market to transfer this energy from the activation of the flexibility. If you can go to the next one, please. But before all of this, I'm going to try to very briefly explain how the wholesale market settlement works and how it is integrated with the local energy markets. So basically, every retailer has a portfolio of clients in step 0. And the retailer is the balancing responsible party for these clients in the wholesale market, which means that the retailer is responsible for procuring this energy, the energy that they deliver in the wholesale market. So basically, the retailer must buy in advance the energy that it expects that the consumers will consume in the wholesale market. This is one side of the story, but the other side of the story is actually metering how much was consumed or produced or delivered, how much was delivered by each consumer on the grid. And this task is done by the DSO. The DSO has access to every meter in the grid, and it knows which one of these meters is associated to a retailer. So the DSO associates, which is the step number 2, the allocation responsible party. The DSO is responsible to allocate this energy that was metered to the retailer. So it basically informs the DSO, the transmission system operator, how much was consumed by each client of the retailer. And basically the DSO is going to sum up everything that was consumed by the retailer's portfolio of clients and compare this with how much the retailer bought on the wholesale market. And any difference is what we call the imbalance. And some things are interesting to point here is that although the retailer must buy this energy in advance, so in forward markets, the whole process of allocating the energy is done after the delivery of energy. And this creates an opportunity for local energy markets within the renewable energy communities, and using the regulation for self-consumption that Bilal just explained, So this creates the opportunity for us to actually have local energy markets that trade energy after the delivery, because this energy is allocated to the retailer after the delivery. So there is this possibility for us to trade energy after the delivery. But this transfer of energy, of course, might generate imbalances, which is what I'm going to explain in the next slide. So in this case, we're assuming there is a post-delivery local energy market, and by definition, the post-delivery local energy market is a market where prosumer B and prosumer A may transfer energy after the delivery. So there is no way the retailer knows about this transfer when the retailer is buying this energy on the wholesale market. So basically, what the retailer is going to do is predict how much the prosumer B is going to consume. So it expects that the prosumer B is going to have a surplus of 200 kilowatts, because in this case, we suppose that prosumer B is generating 400 and consuming 200. So this retailer sold at the wholesale market 200 kilowatts. However, prosumer B sold 150 kilowatts to prosumer A. So in fact, its surplus was 50 kilowatts, and this generated an imbalance of minus 150 kilowatts for its retailer. At the same time, prosumer A, who bought this energy and was expected to consume 300 kilowatts, actually was supplied only 150 by its retailer. So if you compare the imbalances, this local energy transfer between prosumer B and A generated a passive, what we call a passive transfer between their retailers on the same amount, on the same direction. And this is a very interesting principle, because we are going to use this fact to correct the problem that I explained to you before about the energy transfer when there is an activation of flexibility in the local energy market. If you can go to the next slide, please. So I know this is a very scary slide. It's a very complex theme, so I'm going to try to be very simple here. But and this is in fact very repetitive with what I already explained. So in this case, below we have a prosumer associated to a retailer. So this prosumer is within the local energy and flexibility market, and this retailer bought in advance in the wholesale market the energy baseline. In other words, what it expected that this prosumer was going to deliver. But this prosumer was activated by the aggregator, and this aggregator had the flexibility required by the wholesale market, because it had a contract with the wholesale market for flexibility. Then this requesting parties requested for this flexibility, and this aggregator activated the flexibility. The prosumer delivered the delta ED amount of flexibility, so that's what it was able to deliver. And this is basically the imbalance that was generated to the retailer, because it is consuming a different amount of energy than what the retailer was expecting. So what we propose in this local flexibility market is a framework contract between all the agents that operate in the local energy market. And this framework contract basically says that every time flexibility is activated, a contract is automatically signed between the prosumer who delivered the flexibility and a virtual prosumer associated to the aggregator who asked for the flexibility. This virtual prosumer is the aggregator inside the local flexibility market. And this contract is going to transfer precisely the same amount of the flexibility that was delivered. It's going to transfer this energy to the virtual prosumer, who is the aggregator. So why is this interesting? It is interesting because on the retailer point of view, since the energy that was delivered was transferred to the virtual prosumer, there is no impact. The retailer is going to deliver the same amount of energy that was expecting to deliver. And on the aggregator point of view, the aggregator owns, from now on, since the energy was transferred to its virtual prosumer, the aggregator owns this energy that was asked, and therefore it can deliver to the flex requesting parties on the wholesale market. So it owns the energy and can deliver on the wholesale market. So I hope I have convinced you that this is, of course, it's on the conceptual level, but it's an integrated proposal that makes a local energy market, a post-delivery local energy market with a local flexibility market, and also transfer the energy all the way to the wholesale level, to the parties that requested the flexibility without impacting the retailer's position on the wholesale market. And finally, for the conclusions, we believe this is an innovative solution because it integrates local flexibility market. So it's a solution for a local flexibility market integrated with the local energy market. It uses the post-delivery energy market, which is very innovative because it's a very simple energy market where agents, if you imagine very small agents like house owners, they don't have to forecast how much they're going to consume or produce. They basically are going to sell or buy the energy that was already produced. And it is, and it works with the collective self-consumption regulation. So everything we're proposing here can be implemented, of course, with some advances in the regulation, but everything can be implemented in the near future. There is this assumption that we are able to compute the baseline methodologies, and this can be somehow tricky because it is not easy to compute what is the baseline of a specific prosumer, but we assume this can be done as USEF assumes. And also, we think it's interesting because we show that although flexibility contracts are forward by nature because we are dealing the energy that will be delivered in the future. This is the nature of flexibility contracts. This specific point, the compensation of the energy activated is not. This specific point can be solved after the delivery of energy, which makes everything a lot simpler. So I think I hope that we have showed something that is interesting and integrates you. And if you need any references, feel free to contact us. We can deliver. Thank you.
Okay, thank you. So now we have a 10-minute question and answer. So please use the question and answer facility so that I can then read the questions. Just to start it with, we already have 2 questions, but before that, let me just ask you on your opinion about the proximity provision that is included in the legislation. If you consider that this proximity rule is still very restricted vision about the electricity communities, and if in future legislations this should evolve to more general approach.
Yeah, I think it is. For example,
if you have any indication regarding other countries, perhaps in terms of comparison, that would be interesting also.
Yeah, one reason to think that it is a little bit restrictive is the fact that, for example, if you want to set up energy communities in the rural sector, in the agriculture sector, distances are very often larger than the distance that are currently in the regulation. And we are just facing this because we are working with some partners on a proposal for an energy community in the agriculture sector. And this problem of the distance is clearly there, because the facilities, the industry of the agriculture sector, and the generation that can be, for example, in the water reservoirs, very often have larger distance. So this is, for example, one case where this should be relaxed some way.
Okay, so let me now go to the first question. It was not clear to me if the considered approach for the flexibility market for energy communities is transversal to multiple prosumers dispersed among 2 or more aggregators, or the involved prosumers must be allocated to the same aggregator. So I believe this should be to João.
Yes, well, in our example, of course, for simplicity, for the sake of simplicity, we showed an example of one aggregator activating a prosumer associated with another retailer, but we're talking about a local flexibility market, a local energy market, where several prosumers associated to several aggregators are going to be acting. So of course, the important thing here is for us to be able to point out which one was the retailer affected by the flexibility activation, and which one is the aggregator responsible for it. So I don't see a limitation of the number of aggregators acting, but of course we're supposing that it is one aggregator per consumer in this example, but in theory there could be several aggregators acting in this market with several consumers.
Okay, another one for you, I think. Thank you for your presentation. Is it possible for consumers to participate in this market directly rather than going through an aggregator?
The local flexibility market. So, I mean, in the local energy market, for sure, they're participating because it is a local energy market. It's a market where consumers are trading with each other energy. But for the flexibility, we are assuming here it's flexibility required by the wholesale market, but I don't see why they couldn't. I need to understand what would be the need for flexibility for a consumer, but I don't see why they wouldn't be able to as well.
The main problem is the problem of the guarantees you need to have to be able to operate in the wholesale market. So normally the fact that having an aggregator has two explanations. First, that the energy at the household level is a very small amount of energy, and it has no impact on upper level markets. And the other one is that the aggregator normally is a company which is devoted to this and is probably able to pay these guarantees that are needed to operate in these markets. But in principle, they could.
Okay, there is another question that is related with slide 16. So I'm not sure if you want to share the presentation again, slide 16.
16 is this one, so probably it's not this one.
Sorry?
16 is the one I am showing, so probably.
So perhaps not that one, so perhaps the next one, perhaps, I don't know.
Which is the question?
Well, the question is, well, in slide 16, is there any difference between selling 200 kilowatt-hour to the pool or selling 150 directly to another consumer?
Must be this one.
So difference between selling 200 to the pool or 150 directly to another consumer, and then how can we deal with the loss and network facility costs in this framework?
We don't have a pool in this example, but usually when the market is a pool market, if this consumer sells to the pool, he's probably going to sell to someone. So the thing is, we have to identify who bought the energy from him, and the passive transfer of energy is going to happen anyway. It's going to happen because it's going to transfer energy between this consumer and other consumers who might not be the same retailer that this consumer had. What was the second question, Sarabis? I'm sorry.
So, sorry, where is it? How can we deal with the loss and network facility costs in this framework?
Yeah, so actually this trade is not physical. So I know Villar, but in my point of view, this has nothing to do with the use of the network unless this trade implies in some sort of allocation of energy between prosumers, and this allocation uses the grid. But yeah, the self-consumption regulation today, it's advancing in a way in which the renewable energy communities are going to be able to tell the DSO what was the path of the energy between the consumers. And of course, this is going to be translated into use of the grid and therefore paying for the tariff and also for the losses.
Yeah, we have not thought on this, but anyway, the retailer needs to buy what it is effectively delivering, what it is being metered, plus the losses of the grid, of the upper levels of the grid. So probably something similar needs to be thought in the case of selling the energy from these lower levels to the upper levels, but something that we need to think more of this. If it is only some economic problem, you can always use some kind of internal fees to cover this, but there can be also an energy problem, and this is something to think about it.
I understand the question, because in fact, consumer B is consuming less than it was, so it's going to pay less for the grid. But they might have to pay for the use of the grid for the energy that is transferred from consumer B to A. So yeah, this is something that has to be considered by the regulators.
Okay, regarding, let's say, implementation issues, would you say that these local markets will have, let's say, enough liquidity in terms of being attractive for trading? That's the first question. And then how difficult would you say your approach is to implement for a retailer? Would that be the main hurdle?
The first one is the eternal question, and it has not an easy answer. So really, we do not know yet if these markets will have enough liquidity. This is something that needs to be put in place. There are not really many real markets running, so it's difficult to answer. The idea
but
here
perhaps
is
that proximity the rule doesn't help too much.
Yeah, of course. If these rules are too limiting, this won't help a lot. Yeah. The idea here was, in fact, to help on this, because the post-delivery approach is really something very, very easy for the consumers. At the end, they just have to set up a price, which can be set by considering their opportunity cost with the retailer. So they will be willing to buy the energy if it is cheaper, and they will be willing to sell the energy if it is better paid than by the retailer. So for them, it's very easy to participate, and we think that these markets could be very engaging. There are also quite a lot of research on trying to engage participants by exploiting synergies with cross-sector activities. So at the end, participating in these local markets and even in these flexibility markets provides them to some additional benefits, not only economic, so that they are more incentivized. But there is not an easy answer to this question. The second point, I don't remember what was.
So it would be how difficult it would be to implement this approach to retailer.
I don't think this is difficult at all. For the retailer, the flexibility part may imply additional complexity. The post-delivery approach has no impact at all on the retailer. At the end, the retailer just needs to know the self-consumed energy and the supplied energy, and that's all. I don't know if you want to add something, Jean, related to the flexibility part.
It might, of course, that local energy transactions affect the retailer position in of its portfolio. But I think that even this, since the retailer has a big portfolio of clients, even this is going to become predictable somehow with time. And of course, there could be schemes for compensating the retailers for this imbalances that local energy market generates. But I don't think it's going to be this complicated. Not for the retailer, probably for the DSO, but not for the retailer.
I would even add that I think some retailers are just expecting these kind of agreements because they can be worried about the fact that providing flexibility is going to modify their forecast and their commitment in the wholesale market, and this may imply deviations and additional cost.
Okay, so at this moment we don't have any more questions, so I think it's time to pass to the second part of this webinar. So I would invite Alexandre Lucas to give his presentation.
Thank you so much. Actually, I have a question. I was not sure if I would, if I was supposed to write here. Do you mind, Vila?
Of course.
Do you think this would put the retailers in a privileged position to let me rephrase. Do you think independent aggregators would be in the same at the same level if this activity is integrated in a retailer? Could the retailer absorb this uncertainty, this risk, this settlement, this extra settlement, by being himself an aggregator?
Yeah, obviously, if the retailer is the aggregator, this internal contract or internal passive energy is solved. He knows what is going on. The proposal is rather to be applied to allow independency between aggregators and retailers in case the consumers really want to have independent aggregator from the retailer. But obviously, a retailer that aggregates both activities, aggregation and supply, will have these internal transfers already solved.
Okay, so can you now start, Jose?
Yeah, sorry, just had a little problem. Give me a second. Yeah, I thought my laptop was charging, but in fact it was not. Yeah, it's sharing already, right?
Yeah, it's okay.
Yeah, so we've chosen this interesting topic. I mean, and we will approach this through, these are very distinct presentations, so I will present to you probably a more practical one, which is an example of a tool to analyze the pairing of consumers or combination of consumers that are willing to be members of a renewable energy community. So basically, this is to analyze, is a consumer better off with pairing with a given consumer A or a given consumer B. So I will go with you through these points. So just to recap some drivers why people choose to become members of a renewable energy community, some platforms that belong to some projects, European projects that exist to enhance consumer engagement, and how we saw an opportunity to make this pre-analysis and to develop this little tool. We thought that we could find some complementary through load diagrams, and I will explain the hypotheses that we've considered. And I will explain the methodology that we've followed in the project where we developed this tool. Then I will give a bit more focus to the clustering activity that we've developed here, and present to you a case study within this project that I mentioned, and show you the clusters. So in practice, how this can be analyzed, and show you the results. So I've gathered here five reasons why people, what are the drivers for consumers to engage in a hack? So at the top of the list, it's because they have this perception that there might be some financial benefits. Then in second place, there are these the environmental concerns. In third, also the perception that they may increase the thermal performance, the comfort, energy efficiency of their houses. The support of the local community is also an issue here, and to support local projects and businesses. And the last one, basically because they feel that they can increase their security of supply. I present to you here only three. I've been following some European projects. I present to you here three platforms that exist already. So I invite you even to go to the Renaissance project, or even to these references that I have here, the Our Energy. So there are platforms that exist, and they give you the possibility to interact in different ways. So there are three perspectives, I would say, or three categories of platforms. One is the platform that presents to you best practices. Consumers have available a wide range of information about energy communities, what to expect. There are examples of projects. So it's more an information platform. A second type of platforms is probably a more technical one, is where consumers are able to get an estimation of what type of resources could be used, some elements that probably consumers don't know about, allocation factors and so on. And the third aspect is the financial information type of platform, where consumers can have an idea on return of investments or payback times and so on. And why do I talk about this? Because the tool that I'm going to present to you could be easily installed or added to, for example, the last one from the Renaissance project. I actually reached out to this project to invite them to discuss this. So we are still exchanging emails, but could be an opportunity. So the reason why did we come up with this idea of this tool? Because in a project that we were working on, the goal here in Porto, one of the goals was to create a renewable energy community. So right from the start, some colleagues started to, okay, what buildings, what consumers should we choose? How many? How big should it be? So all the natural questions came up. And in fact, we started to say maybe there are consumers that it makes more sense for them to pair with each other than others. So should a given consumer A pair with a consumer B or 2, or consumer 1 should pair with consumer 3? So we started by looking at their load profiles. And we thought that, well, maybe if they are different in terms of consumption, this could bring value to this. So let's investigate a bit. So here in figure A, we have a consumer 1 and 2, and they are quite similar, these profiles. I mean, time-wise, we have under this generic PV generation curve, we have them both under this generation, but we still have a surplus energy here that is not being used. So they're not quite different. Whereas in this second example, we have consumer 1 and 3, where it has the second peak or the second consumer. So it has a different peak at a different hour. And it can take advantage of this surplus energy. In fact, when we then look at the sum of both these profiles, we see that when they are not complementary, in fact, they don't use most of the generation that they have available. And when there is difference, when they are different or they can be complementary, and they can make use of the surplus energy. So it's not so simple as this. I mean, there are other factors to have in consideration, the allocation factor, the type of resources. But to pursue an investigation, we had to go with these three hypotheses. And so the first one, what happens is either these load profiles are very similar, and so a consumer would be better off, when we look at the surplus energy or auto consumption, would be better off by himself, unless there is some kind of economies of scale to install resources in both places. But I mean, there is no advantage to pair with such consumer. There is the second hypothesis, which is that they have different load consumption profiles, but this does not improve auto consumption, because they might consume in different hours. Let's say that a given consumer consumes during the night and the other consumes during the day, and they have PVs, and the other does not take advantage of the surplus energy. Of course, it depends on the resources. Again, we can argue that we can install storage and defer this type of generation or consumption, but then we would be increasing the cost of the installation and not fulfilling one of the drivers that we've seen in the beginning. And then there is this third hypothesis, which is, well, they in fact are different and they are complementary, but we need to prove this, and this is what we try to do with this tool. So I will go through this methodology that we've used in this project. So we've started by gathering load profiles, so the data. We had some issues with GDPR, so some of the data is aggregated at the transformer level or secondary substation, which is not a problem because many of the consumers are commercial entities, and so they have their own private secondary substation, and it's a consumer per se. Then since this was a georeference data, we used the QGIS, so a fantastic tool, and a plugin called PlanHeat, which was actually developed in a Horizon 2020 project. And with this plugin, we gathered data from the census data and statistical data. And if we feed this plugin with population, building age, the year, and so on, we are able to get quite an accurate prediction of what the needs will be. Okay, then taking the load profiles and a bit of feature engineering and adding attributes to our data set, we were able then to identify what were the main variables that contributed to the energy consumption of all these profiles. So we used machine learning regression, extreme gradient boosting, and we identified the feature importance. With this feature importance, we created two data sets because we saw that one was there were time series, but we were able to create another data set with annualized energy, with very few attributes, the number of people under each consumption point. And so we applied two different clustering algorithms to the data sets that we had. So the first one, a very common k-means algorithm, and the other one, the dynamic time warping, to work with the time series. Then we wanted to know, okay, now we have the results, we have two clusters. We want to know how different these load consumptions are. So let's overlap the results and take the ones that both clustering exercises tell us that they in fact belong to different groups. And then in this moment, we were ready to make our simulations and provide suggestions of pairings of the consumers. So a bit on these clustering algorithms. Most of you probably know. For the ones who are not aware, why did we have to choose the dynamic time warping? Because these load profiles, even though they can have quite similar behaviors, if they are deferred in time, the algorithm and Euclidean distance approach will not see this similarity. So these two figures here are quite evident of what the algorithm does. The dynamic time warping, what it does is that it creates the waves, and they can have different lengths. And this is the fantastic thing. It's time invariant because it creates an array and it matches one point with at least another point from the other wave. And in practice, what it does is that it takes these two waves, such as a given wave with size n in a space D and another wave m in the same space D. It creates these arrays and it tries to, this is the default. By default, it uses a squared Euclidean distance as the base metric, and it minimizes all these distances. There are different variants to this problem. I've mentioned here the barycenters or the soft dynamic time warping that have slight changes to this equation, but this is the default one, and I think it would be clear if I present it here. Now, let's look at the practical side and how we use this. So this was used in a project in Asprela, the Asprela district. So we started by inputting all the data into the QGIS, as I explained in all the steps of the methodology. And we've identified 1,411 buildings. This did not correspond exactly to the door number. It corresponded to blocks of buildings. And then we classified all these buildings. We gathered information about the age, as I mentioned before. And we identified where all the secondary substations were, or transformers. And we classified this in two ways: the domestic or the commercial transformers. You see here in this table all the consumption points that we've considered, split it in domestic and commercial. This was quite a hard work because we had to reach out to all of these entities to ask permission to use their data and so on, as you can imagine. So we've ran the extreme gradient boosting regression algorithm, and we were able to identify the feature importance. But as you see here, these features don't give you the direction. So it's always a good idea also to make a partial dependence analysis. As you can see here, for example, let me take people on the minutes of daylight, for example. The more sunlight you have during the day, or minutes of daylight during a day, the less impact it will have in the energy consumption. And this can be understandable because people use less light, there is less public lighting, and so on. Now, we've ran the algorithms and we got the clusters. Now, what did we do after? According to the methodology that I explained before, we've overlapped them. So what does this mean? We looked at the clustering results, which resembles something like this that you see at the bottom. And with the dynamic time warping, we got the zero. Let's consider this as a cluster 1 and cluster 2, or if you will, cluster 0, cluster 1. And if in the two clustering exercises for PTD1, they belong to the same cluster, we said, okay, it matches. If, on the contrary, they belong to different groups, we had different opinions of the clusterings, we call them neutral, inconclusive. So they were not distinct enough. And so we did not consider them in the analysis, but we got over 70% of a match between the two clustering exercises. And then we had to prove that our hypothesis of the complementarity was true. So what we did was, you see here in this table, we paired consumers from the same cluster, 1, which you see in this first column, and consumers also from the same cluster, but in this case, cluster 2. And we calculated the surplus energy against a generic PV curve that you see here. And what we did was we ran this little sum that you see here. So it's the power generated in each observation minus the power used by the users in that same observation. And we saw how much surplus the pairing resulted in. So you can see here that in the third column, when we paired consumers from different clusters, we were able to have on average, a 12% improvement. So less surplus energy, more self-consumption. This is not always true. There were some cases that we found that consumers from the same cluster actually outperformed when paired with another from another cluster. But we were happy to find out that we had a maximum of 36 and that on average, this led to an improvement. You might be wondering about the amplitude, so I thought it was better to clarify that no, we've used the z-score that uses the standard deviation, the distance to the average, and so everything was evened. Now this tool, now that I've explained it to you, this tool could be included in the third one that I showed you in the beginning. I gave you 3 examples, there are many more. This would be an easy integration in such a platform. This belongs, it's the energetic platform, belongs to the Renaissance project. And here, consumers would be able to understand if it makes more sense to pair with some type of consumers or other types of consumers, given their assigned cluster. There is the concern, of course, of sharing their own data, but the platform, you could submit your data to the platform and the platform could inform you instead of sharing the data with people that you don't know. And then, I mean, this platform is already very informative. It has data on temperature, on the household consumption as well, but it misses this bridge to engage people with each other, which is, we are both willing to integrate a renewable energy community or one that exists already, or there is a group interested, but is it just because we are all willing to engage in a renewable energy community that makes sense, or is there something else? So I think these tools such as this one, very simple, can improve a pre-analysis and can help consumers to take a more informed decision when going on board with the community. So I just have to give my acknowledgements to Salvador Carvalhosa. He did fantastic work. He's a PhD student. He is a collaborator with INESC TEC. He's a researcher in INESC TEC. So congrats for his work. And now I'm open to your questions.
Okay, thank you. So At the moment, we don't have any questions, so please, if there are some questions, please write them on the question and answer. Just to start with, let me just ask you to clarify, let's say, who would be in charge to run this kind of simulation? Because I suppose that this data, they would only be available at the DSO level or the retail level, and eventually there might be some kind of consumer that might be interested in pairing with some other, and that leads to a second question. From, let's say, a legal point of view, what do you mean by pairing? Because when taking, for instance, your example using the Forlada area, you may be pairing a consumer in one side of that area with another one that is on the other side, and that is not in accordance with the JET legislation, namely the proximity condition and so on. So what is the legal meaning of pairing?
This is a good observation. In our case, in the Asprella project, the district or the campus, it fits with the requirements of the distance. So I think we have about 2 kilometers wide and about 1.6 kilometers height in terms of the map, when we look at the map that I showed you. Now, how to implement this? You were suggesting at the DSO level. Well, I was suggesting that these platforms that exist already to support consumers could implement such tools. So I've actually reached out to this Renaissance project to see if they were interested in looking at this. And these platforms exist. The technology is there, and this type of analysis could be done in such platforms. And it could actually be an incentive and clarify consumers that could be willing to join a renewable energy community. But they have to know if there is any value added at the beginning or before making this choice, not finding out later. So this could improve the information when taking this choice. Now here the pairing was, we referred to pairing because we were considering two, no? But these two can be groups, smaller or larger. In fact, for GDPR reasons, we did not go to individual household level, but in some cases we didn't need. We were talking with we were considering data from supermarkets, from hotels, from universities, and I mean, in terms of compliance with the proximity elements of the legislation, this could be an input of the platform to say, where are you?
Yeah, so in order to restrict the analysis.
Yeah.
Okay, we have now some questions. So the first one, could these pairing models be coupled with demand response so that the PV mismatch is further reduced?
With demand response so that the PV mismatches.
That is the part that you are not in fact using in terms of the consumers that you are pairing.
I mean, I assume we are talking about implicit demand response here, no? Yeah, but I think this could have an impact on the analysis, but now I'm not sure if the colleague is referring to.
There is a further. I think there is a further clarification from this colleague. So what I imagine that is meaning is that if imagine that you pair two consumers, and in a given hour, in any case, even when after combining those two diagrams, there is an excess of PV generation, and so you transmit some sort of a signal in order for those two consumers to connect some more appliances.
Yeah, that's a good idea.
Which
I
means
think it
that
could-
in fact you reduce your the power that you are injected into the network freely.
Yeah, well, there's only so much elasticity that the demand can have, but I think it's a pertinent observation, and it could, to some extent, be used. Yes, I would say yes. Yeah.
Okay, there is a second one. Would the clusters improve if you also consider the complementarity with generation, that is photovoltaics, for instance, instead of just considering the distance between every pair of consumer profiles?
You
I'm
can
not
see
exactly sure about this question, because I mean, this is a more or less restricted geographic area, which means that photovoltaics should not be, let's say, so different. It could be different regarding the number of PV panels, but let's say that the available primary resource should be basically the same.
Yeah.
Because you are not talking about an installation in the north and another in the center. You are talking about the restricted geographic area.
Right.
But I'm not sure.
Yeah. The thing with chat rooms is that we don't have any the possibility to inquire further on the question. If you also consider the complementarity with the generation, I mean, I will answer this probably in a more open way. So hopefully that I can answer to the colleague. I mean, we considered here a generic PV curve and this complementarity, and this third hypothesis that we tried to prove depends on the resources. It's a conversation that I've had with other internal colleagues, and it depends on the resources. Of course, there are typical decisions that one takes in a renewable energy community, and the PV generation was chosen because we believe it's a typical asset that communities integrate. But again, we have to keep in mind what are the drivers. The drivers are that we've seen in the beginning. They see a financial benefit. They want security of supply. They want to consume resources locally. And so this is what we want to maximize, is to see if difference can bring complementarity, and if this complementarity can increase auto-consumption and justify the pertinence of a consumer to be part of a renewable energy community. Because, I mean, I don't think that everyone should be in a renewable energy community. It doesn't, they should be in a community if it makes sense. It's not the solution for everything. And if it makes sense or not, we have simple tools such as this one to evaluate beforehand. So this is the main idea.
Okay, thank you. At the moment, we don't have any other question. Is there any comment, Zach, that you want to make? Any final comment before we close?
No, maybe just to add, as Alexander was saying, it depends on the resources, and it would be interesting to see how the use, for example, of storage would modify all this pairing, because obviously the existence of this flexibility may change quite a lot the result.
Yeah, the thing is that we always consider that the dimensioning of the resources is fit to the community, and storage would increase for sure the cost of the infrastructure. So yeah, in very particular reasons, it could be considered. Yeah, it depends on the resources. Thanks for the observation.
Okay.
Okay.
Okay, so perhaps we will close now. We don't have any questions, and neither on the question and answer, neither here on this exchange board. So let me finish thanking for your presentations, and also thanking for the participation of about 60 or 7 people. So thank you very much, and be aware of the webinars, because there will be more webinars in the future. And so we will be glad with your presence and participation. Thank you very much.
Thank you to everyone.
Thank you, everybody.
Bye.
Bye-bye. Bye-bye.